Here is a single line of Verilog code worth $50 million, always at posedge clock. Inside it, a register that should reset to 0 on every cycle. The engineer who wrote it forgot the reset. 18 months later, that one missing line returns from the silicon as a chip that hangs intermittently in customer data centers. $50 million of warranty claims, recall, and lost revenue from one line. A modern AI accelerator at 3 nanometer has roughly 1 billion gates. Behind those billion gates is roughly 2 million lines of Verilog. Behind those 2 million lines is a population of 200 RTL designers, each one responsible for 10,000 lines, each line capable of taking the program down. The RTL designer is the role that turns the architect's spec into something a synthesis tool can actually compile. They live in the editor. 18 months from architecture freeze to first silicon, and most of those days the RTL designer is staring at the same text editor, simulating the same module, hunting the same class of bug. The role that AI has been most loudly predicted to replace, and the one that has not actually been replaced. 4 walls define the RTL designer's job. Every one of them is about predicting what the silicon will do, 18 months before it exists. Wall 1 is RTL Structure. How to partition the logic across pipeline stages, where the registers go, how the data flows. This is the design decision the synthesis tool cannot make. The tool optimizes what is given. The designer decides what gets given. Wall 2 is timing closure. Every signal in the chip must reach its destination flip-flop before the next clock edge. At 3 gigahertz, that is 300 picoseconds. The designer reasons about path delays before any layout exists, picks the pipeline depth, decides where to insert retiming registers. Wall 3 is verification hooks. Every RTL block needs a test bench, assertions, coverage points. The RTL designer writes the design with verification in mind, exposes internal state for debug, adds parity bits and error counters that will save weeks of bring up later. Wall 4 is synthesis preparation. The RTL has to be written in a way the synthesis tool can compile efficiently. The same logic, written 2 different ways, can produce a 40% area difference in the gate-level netlist. The designer learns which patterns the tool likes and which patterns it does not. 4 walls, 2 million lines of Verilog, 1 designer holds the pencil. Wall 1, RTL Structure. The designer is given an interface specification, inputs, outputs, throughput, latency, area budget. Everything inside the box is their decision. Start with the data path, a multiplier that produces 16 bits per cycle. Should it be a single combinatorial block or a 4-stage pipeline? The combinatorial version uses less area but cannot meet timing at 3 gigahertz. The pipeline version meets timing but adds 4 cycles of latency and 400 extra flip-flops. The designer reasons about both, picks one, and commits. Now the control path, a state machine with 7 states, encoded as binary, gray code, or 1 hot. Binary saves flip-flops, gray code minimizes glitches, 1 hot makes the next state logic faster. 3 choices, 3 different downstream consequences for synthesis, simulation, and power. Now the memories, SRAM macros chosen from the Foundry's library. Each macro has a specific aspect ratio, port count, and read latency. The designer picks the macro that fits the data flow, then writes the wrapper RTL that drives it. A typical AI accelerator block has hundreds of these decisions, made in the first month of design. Each one looks small. Together they decide whether the block will hit its area, power, and timing budgets 18 months later when the silicon comes back. Wall 2, timing closure. At 3 gigahertz, a signal has 300 picoseconds to cross from one flip-flop to the next. Subtract setup time, hold time, and clock skew, and the designer has roughly 200 picoseconds of logic delay to work with. About 15 gate stages, the designer reasons about timing before any synthesis has run. Long combinatorial paths get broken with pipeline registers. Wide multipliers get split into smaller chunks. Memory reads get registered. Mux structures get balanced so no input has a longer delay than another. When the first synthesis runs come back, the report lists the worst paths. Each path is a sequence of gates. Each gate has a delay. The designer reads the report, identifies which RTL construct produced the long path, and rewrites that construct. A nested ternary becomes a balanced mux tree. A wide and/or becomes a parallel comparator. A combinational state machine becomes a registered one. This goes on for months. Synthesis runs overnight. The designer reviews the worst pass in the morning, rewrites a handful of modules, kicks off another run. Slowly, the worst-case slack moves from negative 200 picoseconds to negative 50, to 10, to 30. The day timing closes is the day the block is allowed to leave the designer's hands. Every other block in the chip has its own designer doing the same thing, in parallel, for the same 18 months. Wall 3. Verification hooks. The RTL is not finished when it works in simulation. It is finished when the verification team can prove it works under every input the customer will throw at it. The designer writes the RTL with verification in mind. Internal state signals are exposed at the module boundary so the test bench can observe them. Assertions are embedded in the code. Coverage points are inserted at key control branches. Each one is a small extra line that pays for itself 10 times over in debug time. A parity bit on every internal bus. An ECC code on every memory. A counter that increments on every error. A snapshot register that captures the state when an error fires. None of this is required by the spec. All of it is required to debug the chip when it comes back from the foundry and something is wrong at 3 in the morning. The RTL designer also writes the directed tests, a list of inputs that exercise every corner case the designer knows about. Reset sequences, boundary values, back-to-back transactions. The verification team's constrained random suite is the second line of defense. A senior RTL designer is recognized by the verification team within 2 weeks. The code is debuggable, the assertions are correct, the counters are right. The novice designer is also recognized within 2 weeks. The verification team has to write twice as many tests and chase signals that should have been observable from day 1. Wall 4. Synthesis preparation. The synthesis tool is not magic. It takes RTL, applies a sequence of transformations, and produces a gate-level netlist. The quality of the output depends heavily on the quality of the input. A nested case statement compiles to a balanced multiplexer tree. The same logic written as a chain of if-else compiles to a priority encoder. The first version is faster. The second version is smaller. The designer has to know which one matters for this block. A register defined with explicit reset compiles to a flip-flop with a reset pin. The same register defined with implicit reset, the tool may infer the reset incorrectly depending on the standard cell library. The designer has to know which patterns the tool understands. A clock gating intent expressed with a manual AND gate gets removed by the optimizer. Expressed with an explicit clock gating cell, the tool preserves it. The designer has to learn which pattern produces the result they actually want. There are dozens of these idioms. They are not documented anywhere outside the synthesis user guide and the heads of senior designers. New designers learn them by writing code, running synthesis, reading the netlist, and discovering the tool did something different from what they expected. The cycle takes years to master. That cycle is exactly what AI cannot shortcut. There is no training data on which RTL construct produces which gate-level output in this specific tool version at this node. Every node, every tool release, every library shifts the answer. 3 reasons the AI hype cycle has not replaced this role, and the 2-layer winner that profits every time a line of Verilog gets compiled. Reason 1. RTL is a specification language, not a programming language. The designer is describing what the hardware should be 18 months before it exists, with no ability to run it on real silicon and check. Large language models trained on software code do not have the right inductive bias. Reason 2. The feedback loop is hours, not seconds. Edit RTL, simulate for 30 minutes, review waveforms for an hour, edit again. The cost of one bad line compounds across the tool chain. Reason 3. The patterns that work depend on the tool, the node, and the library. An RTL idiom that synthesizes cleanly in one Synopsys version produces 10% worse area in the next. The designer has to track a moving target no training corpus covers. Now the verdict. There are two layers. Layer 1 is the synthesis tool itself. The winner is Synopsys with Design Compiler and Fusion Compiler. Almost every advanced chip in volume production runs through Synopsys synthesis. License fees around $1 to $2 million per seat per year. 200 designers per program, 200 seats. Synopsys takes most of an industry-wide pool of $400 million a year. Layer 2 is Cadence with Genus and Innovus. Roughly 40% of programs use Cadence as primary, 60% use Synopsys. But almost every program uses both. Designs are validated against both flows because the tools find different bugs. Both vendors capture the role in different ways. License revenue scales with designer count scales with chip complexity. No third entrant has reached double-digit market share in 20 years, the most stable duopoly in the chip industry. That is the RTL designer's job. One line, $50 million when it is wrong, 1 billion gates when the program ships. Next episode, the verification engineer. The RTL designer writes it. The verification engineer breaks it. 2,000 person-hours per chip program, finding the bugs before the silicon does. Subscribe so you do not miss it.